Okay. Everybody can see my screen?
Yes.
Okay,
Good.
so this is called L'Hopital's Rule. Um, and it's about doing limits, but it's kind of like another method. In the past we learned, like, look at the first example. Um, Gosh, back in chapter one, if we said evaluate this limit, when you would substitute, you'd get zero on the bottom. Remember, that was like the big bad thing. And so there's different things you could try. Like you might try to factor, um, which is what we're going to do on the first one. So if I were to factor out, let's say, a 2, then I'd have x squared minus 1. And then do you see that you can still factor further?
Mhm.
So if I keep going, 2 x plus 1, x minus 1. And then whenever we would factor, the idea on these was that something would cancel, and then you would be able to substitute. So do you see at this point, I can substitute in -1. I'm going to end up with, let's see, 2 times -2. So the limit equals -4. And we would have done that back in chapter 1. That's a very likely multiple choice question. That could be like number 1 on the AP exam, kind of like, hey, welcome to the exam. This isn't so bad. All good with that? How did we handle limits at infinity? Do you remember?
It was like Bobo, Botan,
Yeah, exactly. So on this one, because the top and the bottom are both just polynomials, you would compare the degree, right? You got a square on top, square on the bottom. So if the degree is the same, do you remember what that means your answer is? You just look at the
it's the constant.
coefficient. So in this case, it's just going to be 3 over 2. So for those, I don't really need a new method. I mean, those are pretty straightforward, right? Okay, look at the third example. If again, we're always thinking about substituting first. If I were to substitute on this one, um, do you see that the denominator would be 0? That's the big bad thing. And remember how we would rationalize on sometimes when there's, I'm gonna write that down. Sometimes when you have square roots, you would multiply the top and the bottom by the conjugate. Oh, there's Isaac.
He gets a
So
90 for the free quiz grade.
I'll tell him that. So if I rationalize, I'm going to multiply the top and the bottom by square root of x plus 2 plus 3. We probably did this less than the other ones, but it was still one of those options. By the way, I'm not going to go through all that because this new method is going to kind of keep you from having to do that. Isaac, I'm glad you made it.
Bye.
Hey, as far as a free quiz grade, I don't know. What do you guys think if you're 6 minutes late? You think that should take off like 20 points?
I think one usually if you're 1 minute late for an assignment, you're already 30 points off because late is 30 point off curve. So
Oh my goodness. That means you're going to get a negative, let's see, 7, 2, 10, a negative 110.
that's
Ooh,
fair.
hope you
Yeah,
can recover from that, Isaac. Okay,
you won't.
so anyway, but that was the method we would have done on this one. And I could go through and do all the multiplication and I would get an answer. Okay, so forget that. So those are all the methods we learned before. But look at the next sentence. It says, not all indeterminate forms. Okay, hold on. Stop right there. What do you mean indeterminate forms? Well, if you were to go back up to the first one, if you were to go back up, when I actually substituted, all I really did was looked at the denominator and saw that I had 0. But if I had substituted into the numerator, do you see that I would have ended up with 0 over 0 when I first substituted? And on the second one, again, if you had substituted, because that's what we always try first, if you had substituted on the top, if you put in infinity, you'd have infinity squared. What's infinity squared? More infinity. And then you would multiply by 3, and so you still have infinity. And then you would subtract 1, and do you see that the numerator would have been infinity? And if I had substituted infinity into the denominator, I would have infinity. Now, granted, I had another method I could try, but that's what I would have got when I substituted. And the same thing for the third one. If at the very beginning I had substituted in 7, the numerator would have been, let's see, square root of 9 is 3 minus 3. I would have gotten 0 over 0. So when I say indeterminate form, that's what I'm talking about. 0 over 0 or infinity over infinity, that's what we call indeterminate form. Okay, why does that matter? Because you can't use this new method. So this is the name of our new method, LHospitals Rule. You can't use the new method unless when you substitute you get indeterminate form. It's very easy to use, but you have to make sure it's that form. If it's not that form, you got to do something else. Okay? So not all indeterminate forms can be evaluated using those algebraic techniques, meaning factoring or substituting or the comparing the degree of the top and the bottom. So that's why we have LHospitals Rule. All right, so here's how LHospitals Rule works. If you have a limit and you substitute and you get either 0 over 0 or infinity over infinity, then that means the original limit, right, this was our original limit, is the same as if you were to take the limit of the derivatives. What? Notice when I say derivatives, I did the derivative of the top separate from the derivative of the bottom. It wasn't like I did a big quotient rule or something like that. Okay, so let me show you how this works. Look at my example. If I were to substitute, put a 0 in for x, on the top I would have e to the 0 is 1. 1 minus 1 is 0. And if I were to substitute into the bottom, I would get 0 over 0. Okay, check. It's indeterminate form. So that means I can use LHospitals Rule. And by the way, sometimes this shows up on multiple choice and sometimes it shows up on free response. And there is one rule if it shows up on free response. When you go to start using LHospitals Rule, you have to remember to write limit. So this is still limit as x approaches 0. But now I'm going to take the derivative of the numerator. Okay, what's the derivative of e to the 3x? Let's see, it's going to be 3e to the 3x. The derivative of the minus 1 is just nothing. Over, now I do the derivative of the denominator. The derivative of x is just 1. Okay, so hold that thought. Do you see what I did? I just took the derivative of the numerator and the denominator separately. Now, can I substitute in 0? Yeah. I can substitute in 0 to the top. Then I'm going to have 3 times e to the 0, so just 3. And since there's no x's on the bottom, there's nothing to substitute, so my answer is just 3. Got the idea? So I can only use this if when I first substitute, I get 0 over 0 or infinity over infinity. And if this were a multiple choice, I probably wouldn't have written this limit part out. I would have just done my derivative and substituted. But you need to remember on a free response, you have to show that you know that when you're doing the derivative, it's still a limit. It's just kind of a notation thing. So I'll always write down limit one time, and then I'll kind of go into, just scratch work, simplify mode. Okay, so look at the second example. First of all, can I substitute in negative infinity? Well, what is negative infinity squared? Isn't it just positive infinity? And in the denominator, if I put in negative infinity, I'm going to have e to the negative of negative would be positive. Tracking with me there? But what is e to the infinity? E is like 2.7. And if I raise that to a giant number, isn't that just an even gianter number? So do you see that this is infinity over infinity? Everybody okay with that? So that means, good, I can use L'Hopital. So limit, in this case, it's x approaches negative infinity. Okay, derivative of x squared is 2x. In the denominator, what's the derivative of e to the negative x? Well, remember, e is itself times the derivative of the exponent. So wouldn't that be negative e to the negative x? Make sure you stop me, you guys, if I lose you or if you're not following. Good so far? Okay? It's harder to read your eyes on Zoom, so make sure you jump up and down, yell, and scream. Okay. Now can I substitute? Well, if I substitute into the top, I'm going to get 2 times negative infinity is negative infinity. If I substitute into the bottom, I've got negative. Remember we said if you plug in negative infinity, you're going to get e to the infinity, which is infinity. And so students tend to ask, well, what about this? If you have a negative infinity over a negative infinity, is that still indeterminate form? Well, yeah, it is, because you could just cancel those negatives, right? So it's like infinity over infinity. Oh no, you mean if I have an indeterminate form and then I do L'Hopital and then I still have indeterminate form, should I just keep going? Yes. Okay, so let's do L'Hopital again. So now I'm going to get lazy. It's still a limit, but I'm just getting lazy. I'm going to do the derivative again. So the derivative of the top is 2. Derivative of the bottom is going to become positive e to the negative x. Good there. And since this is still a limit, now I substitute in. On the top, I just have 2. On the bottom, e to the infinity is infinity. Okay, I mentioned this in class. I don't know if it was recently or longer ago. What does it equal if you have a constant over infinity? Do you remember? Do you remember me saying that before? Okay, no. So the idea is, think about this. If you have, let's say, 1 over 10, and you compare that to, let's say, 1 over 100, which one is a smaller value, 1 over 10 or 1 over 100?
1 over 100.
1 over 100, right? Okay, compare that to 1 over 1,000. That's even smaller, right? So the bigger the denominator gets, the smaller the value of the fraction. So if you have a tiny little number on top, a constant, and it's over a giant number, isn't that value so small that it's virtually 0? So you just need to kind of get in your head, anytime you end up with a constant over infinity, it equals 0. And that's going to come up quite a bit in this L'Hopital rule thing. Okay? So here I ended up with a constant over infinity, and so that's how I knew my answer was 0. Okay? Let's try another one. Now, when I first start this example, I can tell you right now it's going to be a problem, because I'm not going to end up with 0 over 0 or infinity over infinity, because it's not even a fraction. So maybe before I substitute, I need to picture this as a fraction. Do you see that because that e has a negative x, I could picture this as square root of x over e to the x so that it looks like a fraction? Now, substitute square root of infinity over e to the infinity. Okay, great. Indeterminate form. So I can use L'Hopital. So limit as x approaches infinity. Derivative of square root of x is 1/2 x to the negative 1/2. And on the bottom, derivative of e to the x is still e to the x. You know what I think I'll do? Before I substitute, let's clean this up. That x to the negative 1/2, can't I move that to the denominator? So in fact, I can move the 2 down also. This is kind of like a 1 over 2 square root of x e to the x. That's just me kind of moving things around. Okay, so far? Now when I substitute, if I plug in infinity on the top, all I have is 1. And if I plug in infinity on the bottom, well, 2 times the square root of infinity times e to the infinity, isn't that just a big old whopping infinity? Which actually equals 0. Do you know what I mean? That's going to kind of show up a lot on these. So, for L'Hopital, sometimes when you substitute in, you get your answer right away. Sometimes you have to do it multiple times, like we did on the last example. Sometimes, like on this one, you have to make it look like a fraction first so that it does look like indeterminate form. Okay, look at the next example. If I were to substitute right now, I would have 1 over 0 minus 1 over 0. By the way, That does not equal 0. Let me just write that down. If I were to substitute right now, I would have 1 over 0 minus 1 over 0. That's undefined. You can't have 0 in the denominator. It's not indeterminate form. You can't say, oh, look, I'm subtracting the same thing, because that's not the same thing. So that doesn't help me. So why don't I combine these into one fraction so that I can see if it's indeterminate form? Get a common denominator. I think I've mentioned this before, but I'll say it again. I think the easiest way to add fractions is to consider the denominator to be just the multiple of the two denominators. So it's natural log of x times x minus 1. If you do that, it's easy to get the numerator because the numerator is just going to be the diagonals. The first diagonal, 1 times x minus 1, x minus 1. And then because this one was subtraction, I'm going to keep it subtraction. And the second numerator is going to be the other diagonal, which is just natural log of x times 1. So if I were to get a common denominator, that's what I would have. Let me stop for a minute. Everybody okay with that? And so now, if I do the limit, if I plug in, remember we're plugging in 1. By the way, that from the right, remember that doesn't affect anything you're doing until you get to the very end and nothing works. So that from the right doesn't bother me. So if I plug in 1 minus 1 minus the natural log of 1, isn't that 0? And on the bottom, if I plug in a 1 right there, isn't that going to be 0 times 0? Oh, great. It's indeterminate form. So I can use L'Hopital. All right, so I'm going to have the limit. It's still x approaches 1 from the right, but again, that from the right is probably not going to affect anything. Derivative of the top is going to be 1 minus nothing minus, when you're at home on a snow day, do you still remember the derivative of natural log of x?
1 over x.
Yay! 1 over x. Hey, how am I going to have to do the derivative? If I have natural log of x times x minus 1, I'm going to have to do a product rule, which you're like, oh, that's terrible. It's not that bad. I can see it in your eyes, Peyton. Okay, here we go. Product rule. Derivative of the first, 1 over x, times the second, which is x minus 1, plus the first, natural log of x. Derivative of x minus 1 is just 1. And by the way, don't worry about trying to clean this up. Let's substitute. I might not need to clean it up. Okay? So if I plug in a 1, on top I'm going to have 0. And you're like, oh no, wait a minute. On the bottom, if I plug in a 1, I'm going to have what? 1 times 0 plus 0 is 0. Oh no, does that mean I have to do L'Hospital's rule again? Yes. That's all right. On the top. What's the derivative of 1? Nothing. Do you remember the derivative of 1 over x? Remember how I said, like on day 1 of calculus, hey, here it is, don't ever forget it. Wasn't it negative 1 over x squared? But because of that minus, isn't it going to be positive 1 over x squared? Now, before I do the derivative of the bottom, let me clean this up. If I were to distribute this, 1 over x, wouldn't I have 1 minus 1 over x? I think it'll be easier to do the derivative of it like this, because now I don't have to do a product rule. So the denominator, nothing. Hey, the derivative of negative 1 over x is 1 over x squared. And the derivative of natural log of x is 1 over x. Again, don't worry about simplifying. Let's substitute. I might not need to simplify. So if I substitute in a 1, I'm going to have 1 over 1. On the bottom, I'm going to have 1 over 1 plus 1 over 1. I think we have an answer. Now, that one we just did is probably, it's definitely the highest difficulty you would ever see, almost so high that you might not ever see one quite like that. But it wasn't that bad. I know it looked terrible, but it really wasn't that bad. And we are not going to worry about, whoops, sorry about that. We are not going to worry about problems like this one, ever. I used to do it all the time, and I've come to realize they never have anything at that level on there, so why do it? And that's it. That's LHospitals Rule. Now, I want to point something out to you. First of all, on the homework, which is 178 and 179, make a note. You can skip 3 and 8. Skip 3 and 8. But don't think that you have to do LHospitals Rule. If you can substitute and you get an answer, then you're done. Or if you'd rather factor something, if it looks like something you can factor, great, you're done. And I'm going to say that because of look at number 7 on the homework. If you have LHospitals Rule in your brain and that's all you're thinking about, you might plug in and get infinity over infinity and then do LHospitals Rule. And it wouldn't be that bad, but when you're taking the AP exam and you see a limit, LHospitals Rule is not necessarily at the front of your brain. The front of your brain is this something that is very basic that I can just look at and know the answer to? On number 7, is it? What rule, before we start talking LHospitals Rule, what would you have said how to do number 7?
For the infinity?
Well, it's limit at infinity. Isn't number 7 just like that second example we did at the very top of the notes? And I think, Jack, you're the one who said, hey, that's Bobo Botten. So if you recognize that, forget LHospital. Number 7, you don't have to do. You could, but you don't have to. If you just did your Bobo Botten thing, I can't believe I'm even saying those words. I hate saying that. What would I get?
4.
Yeah, degrees are the same. 4 over 1, because remember you look at the coefficient in front of that squared term. Can't write a 4 like they write a 4. Got to erase that. And so wouldn't it just come out to be 4? So don't think that you have to do LHospital. I mean, yes, the majority of these in the homework are going to be that, but just keep in mind you don't have to do that. All right, so that's it. I'm done with notes. That's your homework. You guys are welcome to, to leave now. I'm going to shut the video off now. Hold on, let me do that.